Imagine waking inside a spacecraft that is already moving faster than anything humanity has ever built. There is no violent shaking, no roar from the engines, no streaks of stars racing past the windows. A glass of water rests quietly beside you. The lights along the cabin walls glow with the same soft warmth they did when the journey began. Air moves gently through the ventilation system, carrying the faint mechanical hum of pumps, computers, and life support machinery. Nothing feels unusual. And yet, far outside the hull, the solar system is disappearing behind you. The sun is no longer the overwhelming source of light it once was. It has become a bright star among other stars, still unmistakable, but shrinking a little more with every passing day. Earth can no longer be seen. The blue planet where every human life began has vanished into the darkness, too distant and too faint for the unaided eye. Somewhere behind you are oceans, cities, forests, voices, and billions of people continuing their lives beneath a sky you may never stand under again. Ahead lies Proxima Centauri, the nearest star beyond the Sun. It is only a little more than 4 light-years away. On the scale of the Milky Way, that distance is almost nothing. Our galaxy stretches for roughly 100,000 light-years. Proxima Centauri is practically a neighbor. But for a human spacecraft, even this nearest neighbor is separated from us by an ocean of space, so immense that our fastest existing machines would need tens of thousands of years to cross it. This ship is different. Its engines have been accelerating for months, pressing the crew gently against the floor with a force close to Earth's gravity. There has been no unbearable launch, no crushing burst of acceleration. Instead, the velocity has grown quietly, second after second, while life inside the cabin continues almost normally. You sleep. You eat. You walk through the corridors. And every moment, the ship becomes faster. At first, its velocity is measured in thousands of miles per second, then tens of thousands. Eventually, it reaches a meaningful fraction of the speed of light. From inside the cabin, there is no dramatic moment when this happens. No invisible barrier breaks. No alarm sounds, simply because the ship is moving quickly. If the windows were covered and the engines stopped accelerating, you would have no simple experiment that could reveal your true speed. You might be drifting slowly through the solar system or crossing interstellar space at hundreds of millions of miles per hour. Constant motion has no feeling of its own. This is one of the strangest truths about speed. You do not feel velocity. You feel changes in velocity. A passenger in a smooth airplane feels the force of takeoff, but once the aircraft is cruising, the body settles. A traveler on a train feels the first pull away from the station, but afterward can stand, walk, and pour a drink, while the landscape moves rapidly outside. A spacecraft follows the same principle. As long as it moves steadily, the people inside remain at rest relative to the cabin. Their hearts beat normally, their clocks tick normally, their thoughts unfold at the usual pace. The ship does not feel fast, and this makes the journey seem almost safe. The engines are performing exactly as expected. Navigation remains accurate. The hull is intact. Internal radiation levels are within their planned limits. Every critical system reports normal operation. There has been no explosion, no mechanical failure, no mistake. But the most dangerous part of this voyage will not begin when something goes wrong. It will begin because everything is going right. The ship is entering a regime no human body, no spacecraft, and no material structure has ever experienced. The faster it moves, the more violently it interacts with things that once appeared harmless. Atoms that would barely touch a slow spacecraft begin striking like high-energy particles. Tiny grains of dust begin carrying the energy of miniature explosives. Light arriving from ahead shifts toward more dangerous wavelengths. Heat accumulates faster than the spacecraft can easily release it, and every additional increase in speed makes all of these problems worse. The darkness between stars is often described as empty. It is not. It only seems empty because we are moving through it slowly. At ordinary spacecraft speeds, the thin gas and scattered dust of interstellar space are almost irrelevant. A vehicle may cross enormous distances without noticing them. But this ship is no longer moving at an ordinary speed. It is beginning to transform the quiet material of the galaxy into something entirely different. The crew cannot see that transformation with their own eyes. Outside, the stars remain silent. The darkness remains calm. But instruments near the front of the ship are starting to detect a change. A little more heat, a little more radiation, a faint but steady stream of impacts against the forward shielding. Nothing severe yet, nothing the ship was not designed to handle. But the numbers are rising, and they will continue to rise as long as the engines continue to accelerate. Because speed itself is not what will destroy this ship. The real danger is what speed does to everything waiting in its path. The idea of traveling near the speed of light sounds violent. It suggests unbearable pressure, a body forced backward into its seat, bones straining under a weight no living thing could survive. In movies, the stars stretch into glowing lines, alarms flash across the cockpit, and the traveler is nearly crushed by the force of acceleration. But speed itself does not work that way. If the spacecraft is moving at a constant velocity, the people inside do not feel that velocity at all. They are not being pressed backward. They are not becoming heavier in their own frame of reference. Their organs are not being pulled out of shape simply because the ship is crossing space at an extraordinary rate. Inside the cabin, everything shares the same motion. The floor, the walls, the air, the crew, and every drop of water in their bodies are traveling together. Relative to one another, they remain at rest. A ball released from your hand falls toward the floor exactly as expected if the ship is producing artificial gravity through acceleration or rotation. A beam of light crosses the cabin. A clock on the wall ticks forward. Your breathing continues at its normal rhythm. Nothing inside the ship carries a label announcing how fast the vessel is moving through the galaxy. This is not a special feature of spacecraft. It is one of the deepest principles in physics. Imagine standing inside a train, moving smoothly across a flat landscape. If the windows are covered and the train does not turn, speed up, or slow down, you cannot determine its velocity by dropping a coin or tossing a ball. The coin falls normally. The ball moves normally. Every experiment inside the train behaves as though the train were standing still. The same is true aboard a starship. Whether it is drifting at 1 mile per hour or 100 million miles per hour, constant motion alone produces no internal sensation. What the body feels is acceleration. Acceleration is a change in velocity. It can mean speeding up, slowing down, or changing direction. When a car suddenly moves forward, your body seems to fall backward because the seat pushes the car beneath you before the rest of your body has fully responded. When the car brakes, your body continues forward until the seatbelt restrains you. A spacecraft can avoid dangerous acceleration by changing speed gradually. If the engines produce a force equal to Earth's gravity, the crew could live under a familiar downward pull while the ship continuously gains velocity. After one day, the increase would be impressive. After weeks, it would be enormous. After months, the spacecraft could be moving at a significant fraction of the speed of light. Yet the crew would experience something close to ordinary gravity throughout the acceleration phase. They might walk through the ship, sleep in beds, prepare meals, exercise. They would feel the thrust, but not the accumulating speed. This distinction matters because it reveals something unsettling. The journey is not dangerous simply because the velocity number becomes large. There is no hidden speed at which the human body suddenly realizes how fast it is moving and falls apart. If the ship could travel through a perfectly empty universe, with perfect engines, perfect materials, and no radiation, then steady motion near the speed of light would not crush the people inside. They could continue moving in comfort. Their clocks would seem normal. Their thoughts would seem normal. Their bodies would age normally from their own perspective. The danger comes from interaction. A spacecraft does not travel through an abstract mathematical emptiness. It travels through a real universe containing matter, radiation, magnetic fields, and gravity. At low speed, these things are gentle. At high speed, their energy relative to the ship becomes enormous. Consider a single hydrogen atom floating almost motionless between the stars. From the perspective of the galaxy, it is simply part of the thin interstellar gas. From the perspective of a rapidly moving spacecraft, that atom is not sitting still. It is racing directly toward the front of the ship. The ship sees the atom approaching at nearly the same speed the ship has relative to the galaxy. The faster the spacecraft moves, the more energetic that encounter becomes. The atom has not changed. The ship has changed the relationship between them. The same is true of dust. The same is true of light. The same is true of every object hidden in the darkness ahead. A slow spacecraft passes through the interstellar medium almost without noticing it. A relativistic spacecraft turns that same medium into a storm. This is the central danger of the journey. Not that motion becomes physically painful inside the ship, but that motion transforms the quiet universe outside it. The darkness does not become more crowded. It becomes more energetic. Every atom approaches faster. Every photon arriving from ahead becomes more intense. Every collision releases more energy into the hull. The crew may remain calm in their seats, unaware of any sensation of speed, while the exterior of the spacecraft begins enduring conditions more extreme than any natural environment humans have ever entered. And this leads to a strange conclusion. The faster the ship moves, the less speed matters inside the cabin, and the more it matters everywhere else. Soon, the engines will push the vessel toward a limit that no object with mass can ever reach. A limit that does not behave like a wall. There is no surface to strike, no barrier to break, only a destination in velocity that moves farther away each time more energy is added. The speed of light is not merely difficult to reach. For matter, it is unreachable. And long before the spacecraft comes close, the price of approaching it begins to reshape the entire journey. The spacecraft continues to accelerate. Hour after hour, the engines convert stored energy into motion. The pressure beneath the crew's feet remains steady, almost familiar, while the sun fades farther behind them. Nothing announces the moment the ship crosses 10% of the speed of light. There is no flash, no shock wave, no boundary painted across the darkness. Only a number changing quietly on the navigation display. 30,000 kilometers per second. Fast enough to cross the distance between Earth and the Moon in less than 13 seconds. Fast enough to reach Mars in under an hour when the two planets are favorably aligned. And yet, compared with light, the ship is still moving slowly. A beam leaving the sun would continue racing ahead at the same speed it always has, 299,792 kilometers every second. The ship may accelerate toward that number, but it can never catch it. This is not because light has a better engine. It is not because photons are lighter spacecraft. And it is not because humanity has failed to discover the correct fuel. The limit is built into the structure of space and time. The speed of light is often described as the speed at which light moves through a vacuum. That is true, but incomplete. It is also the maximum speed at which information can travel. It is the fastest rate at which one event can influence another. If a star were to change in some dramatic way, the rest of the universe could not know instantly. The information about that change would spread outward at the speed of light. Gravity follows the same limit. Electromagnetic signals follow it. Every chain of cause and effect is constrained by it. In that sense, the speed of light is not merely a property of light. It is the speed of causality. And anything with mass must remain below it. At ordinary speeds, accelerating an object is simple to understand. Add energy, and the object moves faster. Add more energy, and it moves faster again. This remains true at high velocities, but the relationship begins to change. Each new increase in speed requires more energy than the last. At first, the difference is small. A spacecraft moving at 10% of light speed still behaves approximately the way classical physics predicts. Its energy is enormous by human standards, but the relativistic correction is modest. At 50% of light speed, the correction can no longer be ignored. At 90%, the energy rises far more sharply than the velocity itself. At 99%, adding vast amounts of energy produces only a small additional gain in speed. The ship continues moving faster. But the speed of light does not seem much closer. This is why the limit behaves less like a wall and more like a horizon. A wall can be struck. A wall can be broken. A horizon remains ahead no matter how far you travel toward it. The spacecraft's rest mass does not increase for the people aboard. A person standing in the cabin still has the same mass they had before departure. The ship's structure does not suddenly become heavier when measured by instruments traveling with it. What rises is the ship's energy and momentum relative to the stars it is passing. And those quantities rise without limit as the velocity approaches the speed of light. To reach light speed exactly, a massive spacecraft would require infinite energy. Not simply more energy than humanity currently possesses. Not the output of every power station on Earth. Not even the energy of an entire star. Infinite energy. An amount with no upper end. The universe contains no engine capable of supplying that. So the final step can never be completed. The crew can move closer to the speed of light, but each attempt to close the remaining gap becomes more expensive than everything that came before. At 90% of light speed, the ship is already carrying more energy than its enormous velocity might suggest. At 99%, its kinetic energy is several times its own rest mass energy. At 99.9%, even a small spacecraft would represent a reservoir of energy, unlike anything ever controlled by human beings. And that energy is not safely locked inside a fuel tank. It is present in the motion of the entire vehicle. Every wall, every machine, every person, every stored meal, and every drop of recycled water. The whole ship has become an object moving with enough energy to make even the smallest collision profoundly destructive. But relativity changes more than energy. It changes the relationship between the travelers, their destination, and the time passing far behind them. To an observer on Earth, the ship's clocks appear to run more slowly as its velocity increases. At 50% of light speed, the difference is noticeable but not dramatic. At 90%, a little more than 2 years pass on Earth for every year measured aboard the ship. At 99%, more than 7 years pass on Earth while the crew experiences one. The people inside do not feel slowed. Their thoughts do not drag. Their hearts do not beat in slow motion. From their perspective, time moves normally. It is Earth that appears to be changing differently. This seems like a gift. Proxima Centauri lies more than 4 light-years away. Even a beam of light requires over 4 years to cross the distance as measured from Earth. A ship moving near light speed could never beat that beam in Earth's frame. But the crew might experience a shorter journey because of time dilation and length contraction. In their frame of reference, the distance ahead becomes shorter along the direction of motion. The star itself has not moved closer in any universal sense. Earth-based observers still measure the original distance. But aboard the spacecraft, the space between departure and destination is compressed. At 90% of light speed, the distance is measured as less than half its original length. At 99%, it appears reduced to roughly 1/7. The travelers may experience only months, where Earth experiences years. For anyone dreaming of reaching another star, this is the beautiful side of relativity. The universe seems to offer a bargain. Move fast enough, and distant places become closer. Move fast enough, and the journey consumes less of your own lifetime. But the bargain has another side. The distance ahead becomes shorter because the relationship between the ship and the universe has changed. The same space that appears compressed still contains gas. It still contains dust. It still contains radiation. All the material spread across more than 4 light-years has not vanished. The ship must still pass through it. And because the crew experiences the distance as compressed, those encounters occur across a shorter span of their own time. More of the interstellar medium arrives each second. More particles reach the forward shield. More energy is deposited into the spacecraft. The apparent shortening of the road does not remove what lies on the road. It concentrates the journey. This is the first sign that the helpful effects of relativity cannot be separated from the dangerous ones. Time dilation may preserve the traveler's years. Length contraction may shorten the path they measure. But the growing energy of every encounter threatens to ensure that neither benefit will matter. The ship can never reach the speed of light. It does not need to. Long before that impossible limit, it has already entered a new physical environment. The instruments begin registering a steady rise in impacts against the forward hull. Each one is microscopic. Most are only individual atoms. There is still nothing visible outside the windows. No cloud, no approaching storm, only darkness. But the darkness is no longer empty, and everything hidden inside the shortened distance ahead is now arriving faster. The first impacts are too small for anyone aboard to feel. There is no sound from outside the hull. No vibration reaches the cabin. No visible flash appears beyond the forward observation cameras. Only the instruments notice. A sensor embedded deep within the ship's protective nose records a tiny pulse of energy, then another, then hundreds more. The events are individually insignificant. Most are caused by single hydrogen atoms. Hydrogen is the simplest and most common element in the universe. Each atom contains 1 proton and 1 electron. It fills the space between stars in extraordinarily thin concentrations, mixed with smaller amounts of helium, ionized particles, and traces of heavier elements. Near Earth, we think of a vacuum as a place almost entirely free of matter. Interstellar space is emptier still. In an average region between nearby stars, there may be only about 1 atom in every cubic centimeter. That is almost nothing compared with the air inside the spacecraft, where each cubic centimeter contains an unimaginable number of molecules. If you could hold a small box of interstellar space in your hand, it would seem perfectly empty. But the ship is not holding one small box. It is sweeping through enormous volumes of space every second. At 10% of the speed of light, the spacecraft moves nearly 30,000 kilometers in a single second. Its forward surface cuts through a long, invisible cylinder of the interstellar medium, gathering every particle lying in that path. The density is low. The speed is not. Every second, vast numbers of atoms strike the front of the vehicle. At first, the shielding manages them easily. The atoms carry little mass, and the ship was designed with layers of material intended to absorb their energy. But the crew notices the trend. As the velocity rises, the temperature near the forward shield rises with it. Radiation monitors begin detecting more energetic secondary particles. The outermost layer of protective material develops damage too small to see from inside, but large enough to measure. The ship is not simply moving through space anymore. It is driving into space. Imagine walking slowly through falling rain. Each drop touches the skin gently. Now imagine moving through the same rain in a fast car. The drops strike the windshield harder, arriving more frequently because the vehicle is sweeping through more air each second. Interstellar gas behaves in a similar way, except the speeds involved are millions of times greater, and the particles do not remain harmless droplets for long. At 50% of the speed of light, a hydrogen atom no longer resembles ordinary gas from the ship's perspective. It approaches like a high-energy proton. The electron may be stripped away during the interaction. The proton penetrates the surface and transfers its energy to the atoms inside the shielding. It can knock those atoms out of position. It can break chemical bonds. It can alter the microscopic structure of the material. The damage does not always appear as a crack or a hole. Often, it begins invisibly, inside the crystal lattice of a metal or the molecular framework of a composite. Atoms are displaced from the positions that give the material its strength. Tiny defects accumulate. Thermal conductivity changes. Electrical behavior becomes less reliable. A surface that looks intact may already be becoming weaker. This is one of the most dangerous qualities of radiation damage. It does not always announce itself. The ship may continue operating normally, while the materials protecting it slowly lose the properties they were chosen for. The forward shield is engineered as a layered structure. The outer layers are intended to absorb the first impacts and carry heat away from the most sensitive systems. Beneath them are denser materials designed to slow energetic particles. Deeper still are layers intended to capture some of the radiation created by the collisions. But each layer has limits. As the ship passes 50% of the speed of light, the incoming particles become increasingly difficult to treat as ordinary matter. They are now part of a particle beam, not a beam created by a machine, and not one coming from a single source. The ship creates the beam through its own motion. Every atom lying almost motionless in interstellar space is transformed, in the ship's frame, into a projectile arriving from directly ahead. The darkness itself has become an accelerator. At 90% of the speed of light, the situation changes again. A proton striking the forward hull at this velocity carries enough energy to ionize material along its path and trigger a chain of secondary interactions. It may penetrate the first layer. It may collide with a nucleus inside the shield. That collision can release fragments, electrons, photons, and other particles, each continuing deeper into the spacecraft. The original proton is no longer the only threat. One incoming particle can become many. The shield absorbs part of the energy, but it cannot make the energy disappear. It can only spread it, redirect it, convert it into heat, radiation, and structural damage. Outside, there is still no visible storm. The stars remain sharp points of light. The cameras show darkness. But the front of the ship is being struck by an invisible torrent. Every second, particles arrive with energies similar to those studied in radiation laboratories and particle accelerators on Earth. The difference is that laboratory beams are controlled. They are switched on for limited periods. They strike small targets inside heavily protected facilities. This ship is exposed continuously, hour after hour, month after month. Across distances measured in light years, there is no pause between experiments. No maintenance team can step outside and replace the target. The forward shield is the target, and the experiment ends only when the ship slows down or the shield fails. The crew begins receiving regular reports from the damage monitoring system. The loss is small at first. A microscopic amount of material removed from the surface. A slight reduction in the performance of an outer layer. A minor increase in the radiation detected behind the shield. Nothing yet requires an emergency response. But the rate is climbing. The faster the spacecraft moves, the more particles it encounters every second. And each particle arrives with more energy. These effects multiply one another. Double the velocity, and the ship sweeps through roughly twice as much space in the same time. But the energy of each collision rises even faster. At non-relativistic speeds, kinetic energy grows approximately with the square of velocity. Near the speed of light, it grows more sharply still. This means the total energy deposited into the forward surface can rise dramatically from what appears to be only a modest increase in speed. The difference between 10% and 20% of light speed is not merely a doubling of danger. The difference between 50% and 90% is far more severe. Each step toward the limit makes the environment ahead less forgiving. Eventually, the protective nose begins to glow faintly in infrared images, not because it is burning in air. There is no air outside. It glows because the steady bombardment is heating it from within. Cooling systems draw the heat deeper into the ship and carry it toward the radiators. Pumps increase their output. Thermal control software adjusts the flow of coolant. The ship remains stable, but stability now requires constant work. Every system connected to the forward shield must operate without interruption. If a pump fails, heat accumulates. If a sensor gives the wrong reading, damage may spread unnoticed. If the shielding erodes unevenly, one region may become more vulnerable than the rest. The crew cannot simply turn the ship sideways to inspect it. The shield must remain pointed forward because the front is the only part designed to face the oncoming particle stream. The orientation of the entire spacecraft has become a matter of survival. A small navigation adjustment must be performed carefully. Even a slight change in angle exposes surfaces that were never intended to face the full force of the interstellar medium. Antennas must remain protected. Radiator panels must avoid the forward direction. Observation instruments must look through narrow shielded channels or remain hidden behind protective shutters. The ship is no longer free to move through space like an aircraft turning through the sky. It must travel like a needle, always pointed into the storm. And this storm is made mostly of the simplest element in existence: hydrogen, the same element that fuels stars. The same element contained in water and in every living body aboard the ship. Individually, its atoms are almost nothing, but multiplied across years of travel and transformed by relativistic motion, they become a continuous weapon aimed at the front of the spacecraft. The crew begins to understand that the emptiness between stars was never truly empty. It was only gentle because humanity had never moved through it quickly enough. Now, the ship is moving faster, and the universe is becoming harder. Yet hydrogen is not the most frightening thing ahead. Atoms are common, but they are small. Far less common are solid particles, tiny fragments of carbon, silicate, metal, and ice drifting through the interstellar darkness. Most are smaller than a grain of smoke. Some may be no larger than a bacterium. At ordinary speed, they would be dust. At the velocity of this ship, they are something else entirely. The first dust impact appears as a brief white pulse on the forward sensors. It lasts for less than a heartbeat. A warning symbol flashes across the engineering display, then disappears as the ship's systems classify the event and return to normal operation. The crew feels nothing. There is no sound inside the cabin and no visible movement of the hull. Only a small region on the outer shield has changed, a shallow crater, surrounded by material that was melted, vaporized, and thrown outward into space. The object responsible was almost unimaginably small. A grain of interstellar dust, perhaps a fragment of silicate once formed near an ancient star, perhaps a particle of carbon released by a dying sun. It may have drifted through the galaxy for millions of years, carried by stellar winds, supernova shock waves, and the slow motion of the interstellar medium. Before the spacecraft arrived, the grain was nearly motionless relative to the surrounding stars. It was not dangerous. It had no explosive material inside it. It carried no engine and no electrical charge strong enough to threaten a ship. Its danger came entirely from relative motion. From the grain's perspective, a massive spacecraft had arrived at a significant fraction of the speed of light. From the spacecraft's perspective, the grain had become a microscopic projectile. The collision occurs so quickly that the materials have no time to behave like ordinary solids. At low speed, an object striking a surface may bounce, bend, crack, or become embedded. At hypervelocity, the collision becomes something closer to an explosion. The dust grain touches the outer shield. Its kinetic energy is released into an area smaller than the width of a human hair. The grain is heated almost instantly, beyond the point where its atoms can remain bound together. It vaporizes. But it does not vaporize alone. The surface directly beneath it is compressed and heated by the impact. Atoms in the shield are torn from their positions. Some become a cloud of hot gas. Others are ionized, forming a rapidly expanding burst of plasma. A tiny crater opens in the armor. Fragments of the shield spray outward and sideways. A shock wave travels deeper into the material. For a fraction of a second, the point of impact becomes hotter than the surface of many stars. Then the energy spreads. The flash fades. The plasma drifts behind the ship, and the spacecraft continues forward. One crater is not enough to end the journey. The shield was designed to lose material. Its outer layers are sacrificial, built with the expectation that some portion of them will be destroyed before the ship reaches its destination. A single microscopic impact can be absorbed. Even thousands may be survivable. The problem is not one grain. The problem is the distance still ahead. More than 4 light-years separate the ship from Proxima Centauri. Across that enormous path, the spacecraft must pass through an uncertain population of particles. Most are smaller than the first grain. Some are larger. Their exact number is difficult to know because the tiniest particles are hard to detect from Earth, while larger grains are rare enough that average measurements cannot guarantee a perfectly safe path. The interstellar medium is not uniform. One region may be unusually clear. Another may contain material left behind by a passing cloud, a stellar wind, or an ancient collision. The ship cannot assume that every kilometer ahead contains the same amount of dust as the kilometer before it. And at relativistic speed, even a small error in that assumption matters. The energy of an impact depends strongly on velocity. At 10% of the speed of light, a tiny grain can already produce intense local damage. At 50%, the same grain carries vastly more kinetic energy. At 90%, the collision enters a regime so extreme that familiar images of bullets or meteoroids become misleading. A bullet remains mostly intact until it reaches its target. A relativistic dust grain and the surface it strikes are both transformed almost immediately into radiation, plasma, and fragments. A slightly larger particle would be far worse. A grain with 10 times the diameter may contain roughly 1,000 times the mass, depending on its shape and density. That means an object still too small to see clearly could release 1,000 times more energy than the particle before it. The danger grows rapidly with size. A speck comparable to fine smoke might scar the shield. A grain closer to the width of a human hair could damage multiple layers. A particle large enough to be seen with the naked eye, though much rarer, could release energy on the scale of a serious explosive event. At these velocities, there is no meaningful distinction between carrying a weapon and simply carrying mass. Motion supplies the destructive power. Engineers have long used layered shields to protect spacecraft from micrometeoroids and orbital debris. One common principle is to place a thin outer layer some distance ahead of the main hull. When a particle strikes the first layer, it breaks apart and spreads into a cloud. The energy then reaches the deeper structure across a wider area, reducing the concentration of the impact. This works well at the velocities encountered near Earth. But a relativistic spacecraft operates in a different regime. The outer layer does not merely break the grain apart. It becomes part of the explosion. The dust and shield material form a forward-moving and inward-moving shower of plasma, radiation, and fragments. Additional layers can spread the damage further, but every layer adds mass. Every kilogram of armor must be accelerated. Every kilogram must later be slowed down. And every additional layer may generate its own secondary particles when struck. The ship could carry a long column of shielding ahead of the inhabited section. It could use water, graphite, advanced ceramics, or replaceable blocks of material. It could release clouds of particles in front of itself, allowing incoming dust to collide with the cloud before reaching the main hull. It might attempt to detect larger grains and destroy them with lasers from a distance. Each idea offers some protection. None is simple. A laser must detect a dark particle early enough to act. The particle may be too small to reflect a useful amount of light. Even if the laser vaporizes it, the mass does not disappear. It becomes a cloud of atoms and plasma, still moving toward the ship at nearly the same relative speed. The collision is spread out, which helps, but the energy remains. Magnetic fields could deflect charged particles. Most dust grains, however, may be neutral or only weakly charged. An electric or magnetic shield cannot reliably push aside every solid object ahead. The spacecraft could attempt to change course, but at near light speed, a heavy ship cannot move sideways quickly enough to avoid something detected only moments before impact. The safest solution would be to know the path in advance. Yet no telescope can map every microscopic grain across 4 light-years of darkness. So the shield continues absorbing what the ship cannot see. Another pulse appears, then another. Most are small, a few are stronger. The damage monitoring system begins building a map of the forward surface. Hundreds of tiny marks appear, scattered across the shield like stars on a dark sky. Over time, some craters overlap. A weakened region is struck again. Heat penetrates more deeply. Sensors beneath the outer armor begin recording sharper bursts of radiation. The shield is still functioning, but it is no longer the shield that left Earth. Atom by atom, impact by impact, the galaxy is rewriting its surface. And the greatest danger may not be the material that the shield fails to stop. It may be what happens when the shield stops it successfully. Because when a relativistic particle collides with armor, its energy does not vanish. The shield can absorb the impact. It can spread it. It can slow the incoming matter. But in doing so, it may create an entirely new storm, one beginning inside the spacecraft's own protective layers. The next collision begins in the outer armor. A proton enters the forward shield at nearly the speed of light, relative to the ship. It passes through the first layer so quickly that the atoms inside the material have almost no time to respond. Then it strikes a nucleus. For an instant, the collision releases energy into a region far smaller than a living cell. The nucleus breaks apart. Fragments scatter in different directions. Electrons are torn free. Gamma rays flash outward. Neutrons, carrying no electrical charge, continue deeper into the shield. The original proton has been stopped, but the danger has not. It has multiplied. This is the hidden problem with protecting a spacecraft from relativistic particles. A shield does not simply catch an incoming proton the way a wall catches a thrown stone. At these energies, matter behaves differently. The shield becomes the site of a particle collision. And one particle entering from outside can create an entire shower of new particles inside the armor. Some of those secondary particles lose their energy quickly, Others travel much farther than the proton that created them. Charged particles can often be slowed by repeated interactions with electrons and atomic nuclei. But neutrons are harder to control. Because they carry no electric charge, they can pass through material without being deflected by the electrical forces that stop many other particles. Eventually, a neutron may strike another nucleus. That collision can release more radiation. It may knock additional neutrons free. It may create unstable atoms that continue emitting radiation after the original impact is over. The shield can become temporarily radioactive. A collision lasting less than a billionth of a second may leave behind material that continues releasing energy long afterward. Gamma rays create another difficulty. They have no mass and no electric charge. Dense materials can reduce their intensity, but no practical shield stops all of them. Each additional layer absorbs part of the radiation. Each layer also becomes another place where energy can be converted into secondary particles and heat. The crew lives behind a carefully designed sequence of materials, each chosen for a different purpose. Low-density layers help spread the first collisions. Hydrogen-rich materials can slow some neutrons. Dense metals absorb part of the gamma radiation. Water stored around inhabited compartments provides both life support and additional shielding. Fuel tanks may be positioned between the crew and the forward hull. Even waste materials can become useful barriers. In an ordinary spacecraft, this arrangement might provide significant protection. But the incoming flux here is not ordinary. The ship is continuously transforming the interstellar medium into radiation at its own front surface. Every meter traveled brings new atoms. Every second produces new collisions. Every collision transfers more of the ship's kinetic relationship with the galaxy into heat, structural damage, and penetrating particles. The forward shield begins to resemble the target inside a particle accelerator. Except this target cannot be replaced at the end of the experiment. It must remain in place for the entire journey. Radiation sensors are positioned throughout the ship. The outer instruments register violent spikes. The inner instruments record smaller pulses, delayed by the time required for secondary particles to move through the shielding. Most remain below emergency limits. But the average level is rising. The crew rarely notices a single event. What matters is accumulation. Radiation damage in biological tissue is measured not only by how much energy is deposited, but by where and how that energy arrives. A low-energy photon may interact with a small number of molecules. A heavy particle or energetic nuclear fragment can leave a dense trail of ionization through cells. Along that trail, electrons are stripped from atoms. Chemical bonds break. Proteins change shape. DNA strands are cut. Sometimes the cell repairs the damage correctly. Sometimes it dies. Sometimes it survives with an error. Over years, those errors may become cancer. Inside the ship, the crew quarters are placed as far behind the forward shield as possible. Sleeping areas are surrounded by water tanks, food stores, and other supplies. During periods of elevated radiation, the crew may retreat into a smaller central shelter. But no shelter can be infinitely thick. The ship must carry every kilogram from Earth, and mass is the trap hidden inside almost every proposed solution. A thicker shield blocks more radiation, but a thicker shield makes the spacecraft heavier. A heavier spacecraft requires more energy to accelerate. If the propulsion system carries its own fuel, more energy usually means more propellant. That propellant also has mass. The ship must accelerate the fuel needed to accelerate the shield. It must also carry the fuel needed to slow the shield at the destination. The solution begins expanding around the problem. Add protection, and the vehicle becomes harder to move. Use more powerful engines, and they create more waste heat. Build larger radiators, and they add more mass and vulnerable surface area. Increase the ship's size, and its forward cross-section may encounter more particles. Every improvement affects something else. There is no isolated subsystem aboard a relativistic spacecraft. The shield changes the propulsion requirement. The propulsion system changes the thermal requirement. The thermal system changes the surface area. The surface area changes the exposure to impacts. The shielding itself changes the radiation it produces when struck. This does not mean protection is useless. A carefully designed shield could make travel at a modest fraction of light speed more survivable, especially for a small robotic probe. But a crewed ship is not small. It must carry air, water, food, machinery, medical equipment, spare parts, living space, and the people themselves. It must remain functional for years. The protection cannot merely prevent immediate destruction. It must preserve the physical structure of the ship, the electronics, the life support systems, and the biology of the crew across the entire route. The outer armor is designed to erode. The deeper shield is designed to absorb. But every absorbed impact leaves something behind. Heat, displaced atoms, microscopic defects, unstable nuclei, secondary radiation. The shield is saving the people aboard. It is also slowly becoming a record of everything the ship has struck. Layer by layer, that record grows. The materials nearest the front become rougher and weaker. Some regions expand slightly from radiation damage. Others become brittle. Thermal stress opens microscopic fractures. Sensors detect small changes in conductivity and density. Repair systems can replace individual sections, but replacement material must also be carried from the beginning of the journey. There is no source of new armor in the darkness. Nothing can be added without first having been accelerated from Earth. Engineers might place disposable shield blocks in front of the main craft. As one layer erodes, it could be released and replaced by another. This would keep the most damaged material away from the inhabited ship, but the replacements add enormous mass. And releasing them safely at relativistic speed creates its own risks. A discarded shield remains in nearly the same path, moving at nearly the same velocity. The ship must ensure that fragments never return or collide with other parts of the vehicle. Another concept is to project a cloud of material far ahead of the spacecraft. Incoming dust would strike the cloud first, breaking apart before reaching the hull. The idea could spread large impacts across a wider region. But the cloud must travel with the ship. If it moves too slowly, the spacecraft catches it. If it spreads too widely, it stops protecting the path. If it contains enough mass to be effective for years, that mass becomes another part of the propulsion burden. Magnetic fields may help redirect charged particles before they reach the hull, but generating a field powerful enough to influence relativistic protons across a useful distance requires large magnets, enormous electrical systems, or both. The magnets add mass. The power systems create heat. Neutral dust passes through largely unaffected. Once again, the solution protects against one part of the storm while leaving another behind. The crew may never see these calculations. They experience the problem through small changes. A radiation alarm that sounds more often. A section of the forward shield marked for replacement. A new limit placed on time spent outside the central shelter. An update to the medical monitoring schedule. A warning that the remaining protective margin is slightly lower than expected. Nothing alone feels catastrophic. The danger arrives quietly, measured in percentages and long-term probabilities. The ship is still moving. The destination is still ahead. The engines may still be capable of pushing faster. But the crew now understands that protection does not remove the violence of the journey. It only determines where that violence is released. Outside the shield, atoms arrive as projectiles. Inside the shield, they become heat and radiation. And beyond the particles, another transformation is already beginning. The light ahead is changing. Stars that once surrounded the spacecraft are slowly gathering toward the direction of travel. The darkness behind is deepening, and the universe itself is beginning to collapse into a narrowing tunnel of light. At first, the change is subtle. A few stars near the front of the ship appear slightly brighter than they did before. Their colors shift almost imperceptibly toward blue. Stars behind the vessel seem dimmer, redder, and more widely scattered. The crew may not notice with their own eyes. The navigation system does. Its star maps require constant correction because the sky no longer matches the sky that was recorded before departure. The stars themselves have not moved into new positions overnight. The spacecraft has changed the way their light reaches it. At ordinary speeds, the sky appears to surround an observer in every direction. Starlight arrives from ahead, behind, above, below, and from every point between. At relativistic speed, that familiar arrangement begins to distort. Light coming from the forward direction is concentrated into a smaller region of the sky. This effect is called relativistic aberration. The faster the ship moves, the more strongly the apparent positions of stars are drawn toward the direction of travel. A star that once appeared far to the side begins shifting forward. Another that was almost behind the ship creeps toward the edge of the forward sky. As the velocity rises, more and more of the visible universe seems to gather ahead. The stars are not physically being pulled together. Their light is arriving at angles altered by the motion of the spacecraft. But to the people aboard, the effect is real. The celestial sphere appears compressed. The darkness ahead becomes crowded. The darkness behind becomes empty. At 90% of the speed of light, the distortion is dramatic. The stars no longer appear evenly distributed around the ship. A large portion of the sky is compressed into a bright forward region, while the rear hemisphere stretches and fades. At still higher velocities, the universe begins to resemble a tunnel, a concentrated field of light ahead, a widening darkness behind. It is beautiful. And it is dangerous. The same motion that changes the apparent direction of the stars also changes the energy of their light. Photons arriving from ahead are blue-shifted. Their wavelengths become shorter. Their frequencies rise. Their energies increase. Light arriving from behind is red-shifted. Its wavelengths stretch. Its energy decreases. This is the relativistic version of the Doppler effect. On Earth, the effect is familiar through sound. A siren approaching on a road sounds higher in pitch. After it passes and moves away, the pitch drops. The source has not changed the note it produces. The motion between source and listener changes how frequently the sound waves arrive. Light behaves in a related way, though the equations are governed by relativity rather than ordinary addition of speeds. A star ahead may emit much of its light in the visible range. As the spacecraft accelerates toward it, that light shifts toward shorter wavelengths. Red light moves toward yellow, yellow toward blue, blue toward ultraviolet. Radiation that was once visible may move beyond the range of human sight and into wavelengths capable of damaging cells and materials. Ultraviolet radiation can shift toward X-rays. X-rays can shift toward still higher energies. The effect depends on the original wavelength and the spacecraft's velocity. Not every photon becomes deadly at once, but the forward radiation environment grows steadily harsher, and the photons do not merely become more energetic. More of them arrive from the forward direction in a given amount of time. The ship is moving into the radiation field. Light that was spread across a wide sky is concentrated into a narrower cone. The result is a forward region that is both brighter and more energetic than the sky the ship left behind. From inside the cabin, this transformation would not be viewed through an ordinary window. A true, transparent window facing forward would be a dangerous weakness in the shield. Instead, cameras and instruments gather information through protected optical paths. Their sensors must be designed to survive the changing spectrum. A camera built to observe visible light may become overwhelmed. Protective filters must adjust. Detectors must be shielded or replaced. The image presented to the crew may be heavily processed, reducing dangerous wavelengths and reconstructing colors that no longer arrive naturally. What they see on a display is not exactly the sky outside. It is a translation. The real sky ahead may be too bright in some wavelengths and invisible in others. Some familiar stars disappear from the visible spectrum because their light has shifted into ultraviolet. Infrared sources move upward into visible light. Objects that were once hidden may appear. Others vanish. The galaxy seems to reveal a different face. Even the background glow of the universe is affected. Every direction in space contains the cosmic microwave background, the faint radiation left from the early universe. At rest, it is extremely cold, peaking at millimeter wavelengths. At the velocities discussed during most of this journey, the forward portion is shifted upward toward shorter sub-millimeter and far infrared wavelengths. It does not suddenly become a wall of hard X-rays at 99.9% of light speed. That would require a far more extreme approach to the limit. But it does become warmer and more concentrated in the direction of travel. And it adds to the total radiation load already created by starlight, interstellar gas, and particle collisions at the shield. The spacecraft is not facing one single source of danger. It is facing an entire sky, transformed by motion. A star that appears harmless from Earth may produce a very different spectrum in the ship's frame. A region rich in ultraviolet light becomes more severe. A distant X-ray source is shifted upward in energy. Light from hot stars ahead becomes more damaging. Radiation from behind becomes weaker, but that offers little comfort. The forward shield is where the pressure is greatest, and the forward sky now contains the concentrated light of much of the universe. There is another consequence. Navigation becomes more difficult. Before departure, the ship carries precise maps of the stars. Their positions are known. Their colors and spectra are catalogued. Their motions through the galaxy are measured as accurately as possible. But those maps were created in the frame of Earth. At relativistic speed, the crew sees a distorted sky. A star may appear in a different position because of aberration. Its color may be shifted far from the value stored in the catalog. The navigation computer must reverse these effects to identify it. To correct the apparent position of a star, the computer must know the ship's velocity. But one method of measuring that velocity is to examine the Doppler shift of known stars. The two problems depend on one another. The ship needs an accurate velocity to reconstruct the sky. It needs an accurate reconstruction of the sky to confirm its velocity. This is solvable in principle. Multiple reference stars, onboard clocks, inertial systems, and continuous measurements can reduce uncertainty. But the calculations must remain precise. A tiny error in velocity produces a small error in the reconstructed position of a star. A small angular error sustained over light years can become an enormous miss at the destination. The ship is traveling toward Proxima Centauri, but it cannot aim at the star's current position. Proxima is moving. The Sun is moving. Every nearby star is following its own path through the galaxy. The destination must be predicted years in advance. The spacecraft must aim not for where the star was when it left Earth, but for where the star will be when the journey ends. Meanwhile, the sky used to guide that aim is being compressed and recolored by relativity. The universe ahead is both the destination and the source of the distortion. As the ship continues accelerating, the forward view becomes more intense. Stars crowd toward the center. Colors shift beyond the range of human vision. Radiation sensors record a growing load. The protective systems close additional shutters. Observation windows that were already narrow become narrower still. The crew sees less of the real sky and more of the computer's reconstruction. The experience is strangely isolating. The universe is all around them, yet the ship must hide from it. The brighter the forward sky becomes, the less safely it can be viewed. The faster the travelers move toward the stars, the more those stars must be placed behind layers of shielding, filters, and software. Outside, photons continue striking the hull. Each carries only a tiny amount of energy, but there are many of them. Some are absorbed, some are reflected, some penetrate into the outer layers, and every photon that is absorbed leaves its energy behind. The ship is already struggling with heat from its engines, electronics, life support systems, and particle impacts. Now the concentrated radiation ahead adds another source. The universe has collapsed into a bright tunnel before the spacecraft, and every part of that light must eventually become either reflected energy, transmitted radiation, or heat. Heat is one of the quietest dangers aboard the ship. It does not arrive as a single impact. It does not flash across a sensor and disappear. It accumulates. Every machine aboard produces some of it. The engines create heat while converting energy into thrust. Computers release heat while processing navigation data. Pumps warm as they move coolant through the ship. Lights, batteries, medical equipment, food systems, and life support machinery all contribute. Even the crew adds heat. Every living body aboard is continuously releasing energy into the cabin. On Earth, excess heat can be carried away by air, water, and the surrounding environment. A building releases warmth into the atmosphere. A power plant transfers heat into cooling towers, rivers, or the ground. A spacecraft between the stars has none of those options. There is no surrounding air, no ocean, no cold wind moving past the hull. The space outside is extremely cold, but cold space does not touch the ship in the way cold air touches skin. The spacecraft cannot simply conduct its heat into the vacuum. The only reliable way to remove it is through radiation. Warm surfaces emit electromagnetic energy, mostly in infrared wavelengths. The hotter the surface becomes, the more energy it can radiate away. This sounds simple. Allow the ship to warm slightly. Let the heat escape into space. But the amount of energy involved makes the problem far more difficult. A relativistic spacecraft needs powerful systems. Its propulsion may operate at levels far beyond anything used by ordinary spacecraft. Even if the engines are extremely efficient, a small percentage of wasted energy can still become an enormous amount of heat. A system that converts 99% of its energy into useful thrust sounds almost perfect. But 1% of an enormous power output is still enormous. That remaining heat must go somewhere. At first, it moves into coolant. Pipes carry the warmed fluid away from the engines, computers, shield, and inhabited sections. Pumps direct it toward large radiating surfaces positioned along the sides or rear of the spacecraft. These radiators are designed to glow in infrared. They release heat slowly into the darkness. The larger the radiator, the more energy it can emit. The hotter it operates, the more rapidly it can release energy. But both solutions create new problems. A larger radiator requires more structure. More structure means more mass. More mass requires more energy to accelerate and more energy to slow down. A hotter radiator reduces the area needed, but it must operate closer to the limits of its materials. Seals weaken. Coolant becomes harder to manage. Thermal expansion places stress on joints and support structures. A small crack can allow coolant to escape. And there is no maintenance crew outside the ship to replace an entire damaged panel. The radiators are also fragile compared with the forward shield. They must have large surface areas and relatively low mass. Thick armor would make them too heavy and would reduce their ability to release heat efficiently, so they are spread wide, thin, exposed. The forward face of the ship is protected by layers of dense material. The radiators cannot hide behind that shield and still release energy effectively. They must face open space. Engineers position them away from the direct direction of travel, perhaps along the sides of the vessel or angled toward the rear. This reduces the number of direct impacts. It does not eliminate them. Particles scattered by collisions at the forward shield can strike the radiators. Secondary radiation reaches them. Tiny grains traveling at slight angles may hit their surfaces. Over time, their outer coatings begin to change. A radiator works best when its surface emits infrared radiation efficiently. This property is called emissivity. Damage, contamination, or microscopic changes to the material can reduce that emissivity. The panel may still appear intact. Coolant may still flow through it, but it releases less heat than before. That small loss creates a slow cascade. Less heat escapes. The coolant returns to the ship slightly warmer. Internal components operate at higher temperatures. Their efficiency drops. Electrical resistance rises in some systems, producing even more heat. Cooling pumps must work harder. Working harder produces additional heat. Once again, a system built to solve one problem begins feeding another. The ship's software responds by reducing power use. Non-essential equipment is shut down. Some scientific instruments are placed in standby. Lighting is dimmed. The temperature inside the cabin rises by only a fraction of a degree, but the trend matters more than the number. A spacecraft can tolerate a short period of excess heat. It cannot tolerate a permanent imbalance. If the ship produces more heat than it can radiate away, then the temperature must continue rising. Slowly at first, then more quickly as systems lose efficiency. Eventually, materials soften, batteries degrade, electronics fail, and the life support systems responsible for keeping the crew alive become unreliable. The crew may be surrounded by the coldest darkness imaginable, while the ship overheats from within. This is one of the great paradoxes of space travel. Space is cold, but cooling in space is difficult. The vacuum provides insulation rather than relief. The farther the ship travels, the more dependent it becomes on every square meter of radiator surface. There may be backup panels folded inside protected sections, but unfolding them exposes new fragile structures to the interstellar environment. Replacement coolant may be stored aboard, but every reserve tank adds mass. Some heat could be stored temporarily in large thermal reservoirs, but those reservoirs eventually fill. Energy can be delayed. It cannot be destroyed. The forward shield adds another burden. Every absorbed proton, photon, or dust impact leaves energy in the ship. Part of it becomes radiation that escapes. Part becomes structural damage, and part becomes heat. As velocity rises, the heating at the front of the spacecraft grows. The cooling system must carry that energy backward toward the radiators while also handling the heat from the propulsion system and the inhabited sections. The entire ship becomes a river of energy. Heat enters at the engines. Heat enters at the shield. Heat is created throughout the interior. All of it must flow toward a limited set of surfaces and leave as infrared light. Any obstruction in that flow becomes dangerous. A blocked coolant channel. A failed pump. A damaged radiator segment. A control valve stuck in the wrong position. On Earth, engineers might shut the system down and wait for repairs. Here, shutting down cooling may mean shutting down life support. Stopping the engines would reduce one source of heat, but the ship would continue moving through the particle and radiation fields at the same velocity. The environment ahead would not become harmless simply because thrust ended. The spacecraft has reached a state where continued survival depends on constant balance. Energy in, energy out. Damage accumulated, damage repaired. There is little room for error. And while the crew watches temperatures rise and fall across the engineering displays, the ship continues crossing millions of kilometers every minute. Somewhere in the darkness ahead may be a particle too large to absorb, a fragment too dark to detect early, a change in the route requiring a course correction. The ship must be ready to respond. But at this velocity, the time between seeing danger and reaching it is becoming frighteningly small. The navigation system is always looking ahead. Long-range sensors search the darkness for reflected light, thermal signatures, charged particles, and any disturbance that might reveal an object in the ship's path. Most of the time, they find nothing. Interstellar space remains almost perfectly black. That darkness is not reassuring. It is the problem. A bright object is easy to see. A warm object can be detected in infrared. A large cloud may absorb or scatter starlight. But a cold fragment of rock, a dark grain of material, or a small frozen body may reveal almost nothing until the spacecraft is dangerously close. The ship is moving so quickly that distance is being consumed faster than human intuition can follow. At 90% of the speed of light, the vessel crosses nearly 270,000 kilometers every second. In 1 second, it travels more than 2/3 of the distance between Earth and the Moon. In 10 seconds, it covers a distance greater than the width of the Sun. A danger detected 1 million kilometers ahead sounds distant. At this speed, it is less than 4 seconds away, and detection is only the beginning. First, light from the object must reach the ship. Then the sensor must notice it. The signal must be separated from background noise. A computer must determine whether the object is real, whether it lies in the spacecraft's path, and whether it is large enough to matter. The guidance system must calculate a new trajectory. Engines or thrusters must respond, and the spacecraft itself must move far enough sideways for the object to pass harmlessly by. Each step requires time, not much by ordinary standards. Perhaps fractions of a second for the computers. Perhaps several seconds or minutes for the ship to create a meaningful change in direction. But near light speed, several seconds represent an enormous distance. The warning may arrive. The decision may be correct. The engines may fire exactly as designed, and the collision may still happen before the spacecraft has moved far enough. This is why reaction time becomes almost meaningless at relativistic velocity. A car can avoid an obstacle because the road ahead is visible and the vehicle can change direction quickly relative to its speed. A spacecraft weighing thousands or millions of kilograms cannot turn sharply. There is no air to push against, no tires gripping a road. To move sideways, it must accelerate sideways using thrust. The amount of sideways displacement begins small and grows over time. If the object is detected too late, even a powerful correction changes the ship's position by only a tiny amount before impact. The vessel may alter its future path. It may not escape its immediate one. This creates a disturbing relationship between detection range and object size. Large objects can often be seen from farther away. Small objects are harder to detect, but they may still be dangerous because of the ship's speed. The more hazardous the smallest particles become, the more impossible it is to identify all of them in advance. No sensor can map every grain of dust across the distance to another star. The spacecraft must rely on shielding for the smallest threats and active avoidance for the largest. Between those categories lies an uncertain region. Objects too large for the armor to absorb safely. Objects too small or dark to detect with enough warning. The ship's route is chosen to minimize that risk. Astronomers study the gas and dust between the Sun and Proxima Centauri. They search for known clouds, debris fields, and regions of unusual density. The chosen path avoids obvious hazards, but a route through interstellar space can never be surveyed with perfect detail. The light used to map the path may be years old. Small particles move, clouds change. Unknown objects remain unknown, precisely because no instrument has yet seen them. So the navigation system continues searching. It does not blink. It does not sleep. It compares every new image with the one before it, looking for a point of light that has shifted, appeared, or grown brighter. The crew receives only the important alerts. Most detections are stars distorted by relativistic aberration. Some are energetic particles striking the sensors. Others are flaws created by radiation damage within the detectors themselves. The computer must distinguish a real object from noise inside instruments that are gradually being damaged by the same journey they are trying to monitor. Navigation is not only about avoiding collisions. The spacecraft must also reach a moving destination. Proxima Centauri does not remain fixed in space, waiting at the coordinates recorded on launch day. It moves relative to the Sun. The Sun moves around the center of the Milky Way. The target system, the spacecraft, and every nearby star are all following paths through a gravitational field shaped by the galaxy. The ship must aim toward where Proxima Centauri will be when it arrives. Not where the star appears to be now, not even where it truly is now. The image reaching the spacecraft is already old, because light takes time to cross space. Navigation therefore becomes a prediction. The ship observes the star's past position, estimates its current motion, and calculates a future meeting point. It is less like aiming at a target, and more like arranging an encounter between two moving objects, separated by light years. A tiny error at departure may seem harmless. An angular mistake too small for a person to notice can grow across trillions of kilometers. By the end of the journey, the ship could pass far from the inner system. It might reach Proxima Centauri, yet miss the region where its planets orbit. Course corrections can reduce that error, but every correction requires energy. Each burst of thrust consumes propellant, or draws power from the propulsion system. The fuel reserved for navigation has been carried from the beginning. Correcting a mistake years into the journey means spending mass that was accelerated through every earlier stage. A navigation error has an energy cost, and corrections must be gentle. A sudden turn would expose the side of the spacecraft to the incoming particle stream. The forward shield must remain aligned with the direction of motion. If the ship rotates too quickly or changes orientation too far, fragile structures along its sides may face the storm. Radiators, antennas, sensors, habitats. The entire craft is shaped around one assumption: danger arrives from ahead. Changing direction means changing where ahead is. The ship must rotate so the shield follows the new velocity vector, then apply thrust without allowing unprotected surfaces to face the oncoming medium. Even a small maneuver becomes a carefully choreographed movement. The faster the vessel travels, the less freedom it has. Its trajectory becomes a narrow corridor through the darkness. Its shield must point forward. Its radiators must remain protected. Its sensors must see through restricted openings. Its engines must preserve enough fuel for later. And every decision must be made before the danger becomes visible. The crew may imagine the space ahead as empty. The navigation computer cannot afford to. It treats every unseen kilometer as uncertainty, every faint signal as a possible threat, every correction as a trade between survival now and survival later. The ship is not flying freely toward another star. It is threading a needle through a path it can never fully see. At these speeds, seeing danger and reaching danger begin to become almost the same event. And every correction must be made by people whose safety depends on systems already being worn away around them. The crew does not experience the journey as a series of equations. They experience it as fatigue, as medical scans, as new restrictions added to daily routines, as quiet conversations in the central shelter while radiation levels rise beyond the walls. The ship's shielding reduces much of the danger, but it cannot remove all of it. Some particles penetrate deeply. Others create secondary radiation inside the armor itself. Galactic cosmic rays arrive from directions beyond the forward path, striking the spacecraft from the sides and rear. These particles are not ordinary radiation. Many are atomic nuclei moving at enormous speeds. Protons, helium nuclei, and heavier elements, accelerated by violent events across the galaxy. A heavy cosmic ray nucleus passing through the human body does not spread its energy gently. It cuts a narrow path through tissue. Along that path, atoms are ionized, molecular bonds are broken, and DNA can be damaged in clusters too complex for the cell to repair perfectly. Most damage does not create an immediate symptom. A person does not feel a DNA strand break. There is no pain when a particle passes through a cell. The consequences may not appear for years. A damaged cell may die. It may recover. Or it may survive with a mutation that slowly changes the way it grows. This is why radiation exposure is measured over time. One event may mean nothing. Thousands of events become probability. The longer the journey lasts, the greater the chance that enough damage accumulates to produce cancer, neurological changes, or failures in tissues that do not repair easily. The nervous system is especially concerning. Many cells in the brain are not readily replaced. A high-energy particle passing through neural tissue can damage cells along a dense track, while secondary particles spread the injury outward. The effect of a single event is small. The effect of years beneath a constant cosmic ray background is uncertain. That uncertainty follows every crew member. Medical systems scan their blood, eyes, bones, and nervous function at regular intervals. Small changes are compared with records from before departure. A new irregularity may be harmless. Or it may be the first visible sign of damage that began months earlier in the forward shield. The ship carries medication, surgical equipment, and automated diagnostic systems, but it does not carry an entire hospital. There is no specialist on Earth who can examine a patient in real time. A message requesting advice may take years to receive an answer. There is no emergency evacuation, no replacement crew, no second spacecraft waiting nearby. The people aboard must treat every illness with what they brought and what they know. This changes the meaning of risk. On Earth, a medical problem may be serious but manageable because help exists beyond the room. Here, every injury must be considered alongside the mission. If one crew member becomes too sick to work, another must take over their responsibilities. If several people are affected, critical systems may lose the human attention needed to keep them functioning. The ship has automation, but automation is not perfect. Machines can monitor, calculate, and respond to expected failures. They are less reliable when several unexpected problems occur together, and the journey is built from interacting problems. Radiation damages electronics. Damaged electronics place more responsibility on the crew. A tired crew makes more mistakes. Mistakes can increase power use, reduce cooling efficiency, or expose the ship to additional risk. The human body is another subsystem in the same fragile network. Artificial gravity may reduce some physical deterioration. During periods of sustained acceleration, the crew can feel a familiar downward force. If the ship rotates during long coasting phases, it may provide gravity in inhabited sections. But artificial gravity does not stop radiation. It does not remove isolation, and it does not change the fact that the environment outside the hull is becoming more hostile with every increase in speed. The crew begins spending more time in the central shelter. It is the most protected part of the ship, surrounded by water tanks, food stores, equipment, and layers of hydrogen-rich material. The shelter is safe by the standards of the journey. It is also small. There are no wide windows, no open rooms, no view of the stars. The faster humanity travels toward another sun, the more deeply the travelers must hide from the universe around them. Days become structured around maintenance, medical checks, exercise, and system reports. A normal routine is essential. Routine gives the crew a sense of stability when the numbers outside the cabin suggest the opposite. Shield thickness remaining. Radiation dose accumulated. Coolant efficiency. Propellant reserve. Estimated arrival error. Each value changes slowly enough to ignore for a day. Together, they describe the shrinking margin between the crew and failure. And still, the destination grows closer. Proxima Centauri is no longer only a coordinate. Its light is brighter. Its position is clearer. The ship has survived the particle storm, the dust impacts, the radiation, and the heat. The crew has survived years inside a machine that could never truly protect them from everything. It would be natural to believe that the worst part is nearly over. But the spacecraft is still moving at an enormous fraction of the speed of light. And reaching the star is not the same as arriving. Even if every person remains healthy, every shield stays intact, and every system continues working, the ship must still solve one final problem. It must stop. Proxima Centauri now dominates the forward instruments. For years, it was only a faint red point buried among other stars. Then it became brighter. Its motion against the background became easier to measure. The navigation system refined the final approach, correcting the ship's path by fractions of a degree. Now the star is no longer distant in the same way. Its light fills the sensors. Its planets, once invisible, begin to reveal themselves through tiny changes in motion and reflected radiation. The crew has crossed the space between suns. They have survived everything the darkness placed in front of them. And yet, unless the spacecraft begins slowing down, they are not truly arriving. They are only passing through. In space, motion does not fade on its own. There is almost no friction between stars. No atmosphere waits ahead to slow the ship. No ocean of gas presses against the hull. Turning off the engines does not reduce velocity. It only ends acceleration. A spacecraft, traveling at 90% of the speed of light, will continue moving at 90% of the speed of light until something acts on it. It could drift for 1,000,000 years and lose almost none of that speed. This is one of the simplest laws of motion. It is also one of the most expensive problems in interstellar travel. Every unit of energy used to accelerate the spacecraft must be dealt with again before the ship can stop. The journey to the star has not ended. It has reached its mirror image. To slow down, the ship must generate thrust in the opposite direction. The engines that once pushed the spacecraft toward Proxima Centauri must now push against its motion. This usually requires turning the entire ship around. The maneuver is slow and deliberate. The forward shield, which has faced the particle storm for years, cannot simply be rotated carelessly into a new orientation. Radiators must be folded or repositioned. Antennas must be protected. Delicate instruments must be secured. The ship's structure must rotate while continuing to travel through interstellar space at an enormous velocity. During the turn, the direction of motion does not change immediately. The ship may face backward while still moving forward. For a brief period, the engines point toward the destination, while the spacecraft continues racing toward it. Then, the deceleration burn begins. The crew feels gravity return beneath their feet, but now the force is directed in the opposite orientation from the acceleration phase. The engine exhaust streams toward Proxima Centauri. The ship begins surrendering the energy it spent years gaining. Slowly, very slowly. The difficulty is not only producing enough thrust. It is carrying the fuel required to produce that thrust. Every kilogram of propellant used for braking had to be brought from Earth. That braking fuel was accelerated along with the ship, and the fuel required to accelerate the braking fuel also had to be carried. This is the hidden multiplication inside every relativistic mission. The spacecraft does not simply carry fuel for the first half of the journey. It carries fuel for the second half, and fuel for the fuel, and structure to contain it, and shielding to protect it. The entire vehicle becomes heavier because it intends to stop. If the ship used all its propellant to reach the highest possible speed, it could arrive near Proxima Centauri quickly. But it would have nothing left to slow down. The star would grow rapidly ahead. The system's planets would appear. The instruments would gather data. Then, almost immediately, everything would fall behind. At 90% of the speed of light, the ship could cross the distance from Earth to the Sun in a matter of minutes. A planetary system is vast by human standards. At relativistic speed, it becomes brief. There would be little time to observe one world, adjust course, and approach another. No chance to enter orbit. No chance to land. No chance to remain. The mission would become a flyby, lasting hours after a journey lasting years. A civilization could send a robotic probe this way and still learn something valuable. A small instrument package might photograph planets, measure magnetic fields, and transmit data back toward Earth. But for a crewed vessel, simply flashing through the system is not arrival in any meaningful sense. The people aboard did not cross 4 light-years merely to watch a new sun vanish behind them, so the spacecraft must slow down. And deceleration exposes it to many of the same dangers it faced during acceleration. The engine produces heat. The radiators must work at high capacity. The crew depends on every propulsion component functioning after years of radiation and vibration. A valve damaged early in the voyage may fail only now. A weakened fuel line may crack under renewed stress. A guidance sensor degraded by cosmic rays may introduce a small error in thrust direction. During cruise, such problems may have remained manageable. During braking, they become urgent. The timing must be precise. Begin too late, and the ship enters the system too fast. Begin too early, and the journey lasts longer, increasing exposure to radiation and system failure. Use too much propellant correcting the trajectory, and too little remains for final capture. Use too little thrust, and the ship misses the intended orbit. The spacecraft must not merely reduce its speed, it must match the motion of the destination. Proxima Centauri is moving through the galaxy. Its planets are orbiting the star. The ship must approach with the correct direction, speed, and timing to become part of the system, rather than an object cutting through it. This requires far more than pointing at the star and braking. The vessel may attempt to use the star's radiation, stellar wind, or magnetic field to assist with deceleration. A magnetic sail could interact with charged particles flowing outward from the star. A light sail might turn the pressure of Starlight into a gentle braking force. These ideas could reduce the amount of propellant carried from Earth, but their performance depends on enormous structures surviving the journey and deploying correctly after years in deep space. And the closer the ship comes to the star, the stronger the radiation environment becomes. The same light that may help slow the vessel also heats its surfaces. The same stellar wind that may provide drag contains energetic particles. The destination offers tools. It does not offer safety. The crew watches the velocity fall. 90% of light speed becomes 80, then 70. The numbers change slowly, despite the enormous power of the engines. The ship has spent years becoming fast. It cannot become slow in an instant. Behind them lies the long corridor between stars. Ahead, Proxima Centauri grows larger and redder. For the first time, the system begins to look like a place rather than a point of light. The braking calculation is working. The ship may truly arrive, but reaching another star has not erased the cost of the journey. It has only revealed its final form. The spacecraft had to survive acceleration. It had to survive the interstellar medium. It had to survive radiation, heat, and years of damage. And now it must survive the act of giving back nearly all the energy that carried it here. Arrival is not where the energy problem ends. It is where the second half of the disaster begins. The spacecraft finally slows. For the first time since leaving the solar system, the destination no longer rushes toward the ship. Proxima Centauri hangs ahead as a true star rather than a brightening point. Its planets move in predictable paths. The navigation system begins calculating stable orbits instead of collision courses. The engines reduce their thrust. The pressure beneath the crew's feet fades. After years of acceleration, shielding alarms, radiation checks, course corrections, and braking calculations, the journey appears to be over. But another distance has opened behind them. Not a distance measured in kilometers, a distance measured in time. Every clock aboard the spacecraft has behaved normally. Every second felt like a second. The crew slept through ordinary nights, counted birthdays, watched supplies decline, and felt their bodies age at the familiar human pace. No one experienced time slowing down. Relativity never feels strange to the person moving with it. The difference becomes visible only when their clocks are compared with clocks far away. Back on Earth, more time has passed. How much depends on the speed of the voyage and how long the spacecraft remained in relativistic flight. The faster the ship traveled, the greater the separation between the time experienced aboard and the time experienced by people who remained behind. For a journey to the nearest star, the difference may be measured in years rather than centuries. For a journey across dozens or hundreds of light years at more extreme velocities, it could become far greater. The effect is not an illusion. The travelers have not merely lost track of Earth's calendar. They have followed a different path through spacetime. Two people who once stood beside one another can depart, move differently through the universe, and later reunite having aged by different amounts. This has already been measured with precise clocks on aircraft and satellites. At human scales, the differences are tiny. At relativistic speeds, they become part of the mission. The crew knew this before departure. They saw the calculations. They signed agreements acknowledging that Earth would continue without them. But understanding a number is not the same as living inside its consequence. The first messages from home arrived regularly. There were updates from families, technical reports, news from Earth, and images of the planet the crew could no longer see. As the distance grew, the delay increased. A message sent from Earth could take years to reach the ship. A reply required years more to travel back. Conversation became impossible. What remained was correspondence across time. A crew member might receive a recording of a child speaking from several years in the past. By the time an answer returned, that child would be older than the person in the message. Questions arrived after the situations that created them had already changed. Advice reached people who had long since made their decisions. Every transmission was a preserved moment. The crew was not speaking with Earth as it existed now. They were speaking with earlier versions of it. And Earth was doing the same with them. During the fastest phases of the journey, messages from home may have appeared to arrive in unusual patterns from the crew's perspective. Years of Earth history could be compressed into a shorter span of time aboard the ship. Governments changed. Technologies advanced. Cities expanded. People aged. Some messages simply stopped. Not because communication equipment failed, but because the person who had been sending them was no longer there. The crew had crossed a distance of only a few light years, yet the social world they left behind had continued moving in a direction no engine could follow. This is one of the quietest costs of relativistic travel. Time dilation can shorten the journey for the traveler. It can make otherwise impossible distances fit within a human lifetime, but it does not preserve the life that existed at departure. Every year saved aboard the ship is not removed from the universe. It passes somewhere else. The faster the travelers move, the more deeply they separate themselves from the time of their home. If the mission returns to Earth, the difference becomes even more severe. The crew may complete a round trip while aging only a fraction of the time experienced on the planet. They could return physically younger than people who were once children when they departed. Institutions they knew may no longer exist. Languages may have changed. Scientific questions that motivated the mission may have been answered decades earlier by other methods. The spacecraft could return as both a triumph and a relic. Its crew would be alive, but the world that sent them would be gone. This does not mean relativistic travel is meaningless. It means the journey changes what arrival means. Exploration has always involved separation. Sailors once crossed oceans without knowing whether they would return. Polar expeditions vanished beyond communication. Early astronauts left Earth knowing that rescue might be impossible. But interstellar travel extends that separation into the structure of time itself. The crew does not merely leave a place. They leave an era, and still they have reached another star. Beyond the hull, a red sun shines on worlds no human being has ever seen directly. Instruments study atmospheres, temperatures, magnetic fields, and unfamiliar landscapes. Perhaps there are only barren rocks. Perhaps there are oceans beneath ice. Perhaps chemistry has followed pathways unknown on Earth. The destination does not need to contain life to justify the journey. To stand beneath another sun, even through the cameras of a protected spacecraft, would change humanity's understanding of its place in the universe. But the voyage would not resemble the effortless passages imagined in fiction. There would be no simple command to engage light speed, no flash of stars, no arrival a few hours later. A massive spacecraft could never reach the speed of light at all. As it approached that limit, the energy required would rise without bound. Long before reaching it, interstellar gas would become a particle beam. Dust would become a series of microscopic explosions. The shield would turn incoming matter into secondary radiation. The sky ahead would compress and shift toward higher energies. Heat would accumulate inside a vessel, with no air or ocean to carry it away. Objects would become difficult to detect early enough to avoid. And after surviving all of that, the ship would still need almost as much effort to stop as it needed to begin moving. There is no single moment when the universe destroys a relativistic spacecraft. There is a cascade. Each increase in speed strengthens several dangers at once. Each solution adds weight, heat, complexity, or new forms of radiation. The closer the ship moves toward the universal limit, the narrower its margin for survival becomes. The speed of light is not a record waiting for a more powerful engine. It is part of the architecture of reality. It marks the fastest speed at which information, influence, and cause can move from one place to another. Anything with mass must remain below it, and the laws enforcing that limit do not need to build a wall in space. They are present in every extra unit of energy, every incoming atom, every grain of dust, every photon approaching from ahead. The universe is not angry with the travelers. It does not resist them deliberately. It simply continues behaving according to the same laws that shape stars, atoms, time, and life. Those laws allow the stars to be reached. They do not promise that reaching them will be easy. perhaps the first visitors to another system will not be human. They may be tiny robotic probes pushed by powerful lasers, carrying almost no mass and passing through the destination without stopping. Larger machines may follow. Some may learn to slow themselves using magnetic sails, stellar winds, or technologies not yet invented. Human travelers, if they ever make the crossing, may move more slowly. They may accept journeys lasting decades. They may travel inside ships, built not for speed alone, but for endurance. The answer to interstellar distance may not be to approach light as closely as possible. It may be to become patient enough to survive the speeds the universe actually permits. Outside the spacecraft, Proxima Centauri burns quietly. Behind it lie billions of other stars. Some are close. Most are unimaginably far away. They are not forbidden destinations. They are simply farther than our stories taught us to believe. And perhaps humanity will one day reach them. Not by defeating the speed of light. Not by forcing the universe to abandon its rules, but by learning those rules deeply enough to travel within them. Slowly, carefully, across the patient darkness between the stars.